Let's take a look at number 106C. We're supposed to be using Simpson's rule. That's what this S stands for, with n equal to 6 here to estimate the value of this definite integral. Now, if we tried to use the fundamental theorem of calculus part 1, we would be in trouble because it would be impossible for us to find the antiderivative of this function, it turns out. You might want to think about that a little bit. See if you can find the function whose derivative is the square root of x to the fourth plus 1. You're going to be looking for a long time. So we're going to use this numerical method, and Simpson's rule, remember, basically, looks at this curve, whatever it looks like. This is not what the graph of this function looks like, but over an interval from a to b, and it breaks it up into n equally spaced subintervals. It has to be an even number of those, by the way, for Simpson's rule, because what it does is it takes two intervals, these first two intervals, and over this interval, it approximates essentially a quadratic function that passes through these 3 points. Okay, and it matches up really well with the graph of the function in most cases. And so it's a powerful method. So we've got regular rectangles, we've got the trapezoid rule, and then we've got Simpson's rule. So let's take a look at this rule. Here it is. You don't have to memorize this, and actually where this deriving this formula is a little bit involved, but if you want to see more in depth, you can certainly Google that and you'll see a solution or a proof of this Simpson's rule. And I can show one for those that are interested. We did the trapezoid rule in, derive that one in the lecture notes. And so this one's a little bit different the way it's derived, but at any rate, you will not be responsible for deriving it, but you will be responsible for using it. Notice the coefficient pattern here, right? The y sub i's are just the f of x sub i's, where these x sub i's are, a plus I delta x, x of 0 being a. And so, notice the coefficient pattern. You got 1, coefficient of y sub 0, 4, coefficient of y sub 1, 2, coefficient of y sub 2, and then 4. And then that alternates 4, 2, 4, 2, 4, 2, 4, and then back to 1. Notice the first and last, the y0 and yn, have coefficients of 1. So, it's just a formula, plug and chug, really, at this point for us in terms of estimating this definite integral. So let's do it with n equals 6, right? And that comes from the subscript here. Delta x is the b minus a, 3 minus 0 divided by n, so 3/6 or 1/2, and I'll just write that as a decimal. So our x of 0 is 0, right? We start with that lower end limit, and then add 0.5, that's 0.5. And then 0.5 more is 1, and then 1.5 for x sub 3, 2 for x sub 4, 2.5, and 3. And you should stop right x sub 6. You should be ending up at that upper limit. If you're not, if your x sub 6 is not 3, something's wrong, right? That's a little check for you. Okay, so now we plug into the formula. We've got delta x is 0.5 divided by 3, and then we evaluate. Y sub 0 is 1 because y sub 0, right, is f of 0. Remember, our function f of x is the square root of the quantity x to the fourth plus 1. So 0 to the fourth plus 1 is, of course, 1, and the square root of 1 is 1. So I'm just going to replace that with 1. And then f of x sub 1, or y sub 1 here, this is y sub 1 here, right? Notice the coefficient we've got is 4, right? 4. Y sub 1 is the square root of 0.5 to the fourth plus 1, plus 2 times y sub 2, or f of x sub 2. So that would be f of 1. So 1 to the fourth plus 1 is 2. So I get square root of 2. 2 times square root of 2. 4 times y sub 3. So plugging in x sub 3 into the function gives me that. 2 times y sub 4. So how did I get square root of 17? Well, x sub 4 is 2. 2 to the fourth is 16. 16 plus 1, get the square root of 17. 4 times y sub 5. Put that in. And then remember the last one, y sub 6 in this case is going to be f of 3. And 3 to the fourth is 81. plus 1 is 82, square root 82. So there it is in black there. And now the trick is a lot of times is to get this correct with your calculator, right? Because you're going to approximate this. And so you want to make sure you don't round off any intermediate results or, at all. And so the way to do it is just to enter it in as one complete expression. And so that's what I've done here in the calculator. Let's get it so it's beside the expression. So you can see I like to put this in parentheses, 0.5 divided by 3. If you can simplify, you can. I mean, that's fine. 0.5 is a half. 1/2 divided by 3 is 1/6. So you could just write that as 1/6 in the calculator. I like to put all that in parentheses. Asterisk means multiply. And then my parentheses for my bracket here. And then I've got a 1 plus 4 and then square root. And they always open up a parentheses. 0.5 to the 4th. Notice I don't have to put that 0.5 in the parentheses like I've got it written out because it's going to do the exponent first and then add the 1. Okay. Close the parentheses on the square root. Plus 2 times the square root of 2 plus 4 times the square root of 1.5 to the 4th plus 1, all in parentheses, plus 2 times the square root of 17, right? That's that part over there. And then plus 4 times the square root of 2.5 to the 4th plus 1, and then plus the square root of 82. So being careful to do all that, hit enter, and you get this, which if I round it to the 5th decimal place, I get this. Be careful with the rounding of these, right? Don't round into the very end. Right? Notice I didn't round out any intermediate calculations. And so you need to be able to do that on the test with a calculator. And so that's one good thing about the graphing calculators, that you can enter in these expressions like this. Okay, so that is how to do Simpson's rule, an example of it. Trapezoid rule and midpoint rule, very similar. You will not be required to know those formulas. You'll be given those on the test, but you do need to be able to use them.